So, good morning, everybody. Looks like we're just closing the doors, so this is a great time to start. So, this talk is a little bit different, and so bear with me. I'm not going to tell you the full ins and outs of it because I don't really believe in doing that. But what this talk is about is how do we design our software? How do we think about giving feedback on designs that other people write, maybe our partner development teams, maybe partner SRE teams, maybe people on our own teams. And how do we make that process human and productive? And how do we use that to make our systems the best that we can be? So, sadly, a lot of our software is not as good as it could be. Hands up, anyone here who thinks that their software is perfect? Nobody, okay. And that is because software, it's all about trade-offs. I don't think perfect software is possible because you're always balancing competing objectives. But hands up here, anybody who thinks that there's some decision in some of their systems that could have been made better. Yeah. Right, yeah, me too, right, definitely. I mean, like every system I've ever worked on, even the ones that I think were really good. There's a lot of knowledge sitting here in this room. There's a lot of knowledge in every SRE team about how to do things right, how to run reliable, maintainable, robust systems. But we don't always get it right when we go to the drawing board and design a new system. So who here actually, whose team actually writes design documents or RFCs? Okay, that's 50-ish% of you, okay. Maybe a little less, okay. Yeah, I mean, that's kind of how I feel about it. That's kind of what teams have looked like as I've made my way through industry. Some teams do this and some teams do not. And I am a very strong believer that unless you work in a very, very, very tiny organization, I might give you a pass, but I think most of us should be writing down our designs for our major changes. So it's the best tool that I think we have to promote shared understanding. Why are we making this change? What are we going to be doing? What new dependencies is this going to add? What's it going to look like? How are we going to run this? If you don't actually state these things clearly, they're just in your head. And you might go away and you might sit down for 3 months or 6 months or a year, and you might produce software that isn't as good as it could be. And that's a shame. That's a loss to us as a profession. Doing design reviews is a very powerful tool to spot problems early. More brains are always better than fewer brains. We're all this sort of mosaic of bits and pieces that we know an awful lot about and bits and pieces that we don't, right? I'm deep in some areas, you're deep in other areas. If I can write down my design, what I plan to do, and get that in front of the expertise of my whole team, partner teams, I can learn a lot. Particularly if I'm writing something that's going to affect your systems or use your systems, it's very likely that there's something that you know that I don't know. Nobody knows everything. And part of, I think, becoming a senior engineer is realizing how little you do know, right? And how little it's possible to know. So spotting problems early when they are cheap and easy to fix, rather than months down the line when you've invested a bunch of time. It's very powerful. One of the other big reasons for writing things down, I think, is to give partner teams a voice. It's all well and good to sort of stand around a whiteboard with a couple of members of your team and bounce ideas off them. That is great, and that is something that we should do, particularly early on when we're working on a new piece of software. I'm not saying that we need to go away and sit in a bunker for 6 weeks and write a huge design before we talk to anybody else. You should talk to people. But when you're at a point where you have a pretty good idea of what you plan to do, it's really good to write that down and put that in front of other teams that you work with. And again, this is why I say that for small organizations, a lot of this doesn't apply. If there's less than 10 of you, maybe this isn't that useful. Most of us are working in much larger organizations where it is useful. Partner teams include not only, say, partner SRE teams or developer teams that we may work with, it's also really interesting to put these kinds of things in front of support teams. They often know things that you don't. They're talking to customers every day, and they're very often overlooked. And obviously, privacy and security teams, if you have specialist people in those roles, are great people to get early feedback as well. Specifically, written designs are really powerful, and they're really powerful for a couple of reasons. First off, they last. Me standing around a whiteboard or me in a room talking, that's one shot. Even if it's recorded, it's less likely to be useful later on because people can't search it, can't find it. Writing stuff down, it gives you this corpus of this history of the major decisions made about a system. And yes, things do diverge over time, but even where things have drifted a little bit, it's much easier coming into a team, ramping up on a system where you can read the sort of the original design doc and then 2 or 3 revisions for major new features that were added. That tends to get you up to speed a lot faster than, poking about and asking people things. I mean, you need to do that too, of course, but, it really helps. So what kind of changes need a written design? Not every change, for sure. If I'm doing a small feature, fixing a bug, doing some minor production change, that doesn't need a written design. If I'm launching an entire new major system, that needs a written design. If I'm doing some piece of automation that may have some risks or may impact another team, or where I'm going to expect other people in my team to understand it and run it, that I think does need a written design. And you kind of get to places in between. My heuristic for whether or not we should write a design down is, it's basically, is this going to require some new monitoring? Is this or some extensive changes to existing monitoring? Is it going to require some new runbooks or extensive changes to existing runbooks? I think those are the kind of changes, the really kind of production impacting changes that we should definitely be thinking about for design docs. And like I say, risk. Wherever we perceive that there's risk, it's great to write things down. So, the risk of your souffle falling. Okay, so structure. I think every organization who does this process has their own kind of structure, but generally it looks something like, what are the reasons for making the change? What alternatives did you consider? Did you look at other tools, other systems that exist? Describe the change, including things like scalability, performance, risks. How does it impact other teams? And what any security and privacy implications that might exist. So this is the really contentious part of this talk. I'm going to say that design review is central to SRE, and I'm going to say that if you work in an organization, a sizable organization, and you are not doing written designs, and you don't have some sort of process for reviewing those between teams, that's not SRE. That's some other kinds of operations work. And that's okay. It's okay not to be SRE. But I think SRE means that teams need to have agency. They need to have a voice in major decisions that are being made about the systems that they run. And I think that if that is really hard to do without a proper design review process. Because otherwise stuff is just happening in production around you. It's sort of just being thrown at you without full understanding of what that change is, or really having any voice in shaping that change. That's, like I say, that's fine, but that's some kind of different version about operations, right? Because SRE is about having agency. It's about having, the power to sort of push back against things that seem problematic to your production systems. So I think this is really important. And I think any teams that are not doing this, I'm particularly thinking about the sort of the classical model here where you have, some critical business system which has a team of SREs looking after the production environment and a team of developers making changes. If you're in that setup and your developers are making large changes and launching things without talking to you, or the other way around, if you as an SRE team are making major changes or making sort of major reliability improvements or writing, major pieces of automation without checking in with the devs, like you're all kind of working at cross purposes, and that's not an effective way to work. Because remember, you know things that they don't about production and reliability, and they know things that you don't about their system. It's their system and they wrote it, right? So everyone needs to talk to each other. Okay, so here we get into the bad part. I've reviewed a lot of designs over the years, and I tell you, it's really time-consuming, and it's a bit stressful. And as an author, I've written designs as well, and it's not always easy to put your thoughts on paper and put it out there for criticism. So this is a hard process. It's time-consuming, and it's hard on a technical level, and it's hard on a human level. It's all about our ego and our feelings, and it's pretty terrible, right? But it's terrible but necessary. So how can we do it better? Okay, so it is not about showing that you are the best in the world. Maybe you are the best in the world, one of the 100 or so of you here. If so, great. The rest of us are not you. I am not the best in the world. If I'm reviewing someone's design doc, I will do it to the best of my ability, but there will be things in there that I will not see. If I write a design doc, I will do it to the best of my ability, but there will be things in there that I will get wrong. We all need to be able to park our egos at the door and to, sort of help lift each other professionally without trying to make it about scoring points. So what that means is, whenever we're giving technical feedback on another design, confine it to things that are important. Confine it to things where you can give a logical justification for why something is clearly better, or even where there's a trade-off that maybe the author didn't talk about or didn't describe, right? What's really unhelpful, what we need to avoid is debating matters of taste, debating the color of the bike shed or the cocktail, That kind of stuff, it can drag on for a long time, and it's not productive. This is not about matters of taste. This is about, big meaty concerns. That's mostly what the rest of this talk is about. So, something completely different. Who has read the checklist manifesto? Okay, like maybe 5% of you. Okay. It's a good book. It's by Atul Gawande. Atul Gawande is a surgeon. And so he did some studies, and he discovered that, hey, doctors get a lot of stuff wrong. So if you are in hospital in intensive care, you are having something like 178 distinct actions done to you each day. And that could be anything from checking your blood pressure to administering medication to, cracking your chest open and, like sticking things in your heart. Doctors make on average an error about 1% of the time when they're doing these sort of complex procedures. So 99% accuracy and 1% error is very good for a human process. It's extremely good. But unfortunately, if you're having 178 things done to you in hospital every day, that's still about 2 errors per patient per day. And that is enough to kill quite a lot of people or cause a lot of surgical complications or infections that don't need to exist. So Gawande said, right, we're doing well here, but as a profession, we need to do better. What do other professions do to control these kinds of complex processes? So he looks at aviation, and he looks at other professions as well, like civil engineering. They use checklists. And checklists sound super boring, but I'm going to hopefully persuade you over the rest of the talk that they are not. So there are 2 kinds of mistakes that humans make. And we are humans, so we make these mistakes. The first kind is ignorance. I make a mistake because there is something I do not know. I am not an expert in some particular aspect of something, and I just overlook something. I don't know it, right? And then ineptitude. Like, I know something perfectly well, I just fail to think of it or fail to do it in the moment or at the time needed, right? Errors of ignorance, apart from sending someone back to school to study a thing for however many months or parking them in front of a book, errors of ignorance are very hard to fix, right? Those are probably always going to be with us. But errors of ineptitude you can fix because that's something that you should have gotten right, but you got wrong. So one of the examples from the checklist manifesto is about inserting a central line. So inserting a line into one of somebody's blood vessels. There's a few steps to this. First off, you're supposed to clean the patient's skin very, very thoroughly with chemicals. Then what you're supposed to do is you're supposed to drape the patient. You're supposed to clean your own hands and glove up and all this stuff. Make sure that what you're using is sterile and do the insertion, right? So there's several steps to that. And something like 10% of the time when this study was done, doctors were getting them wrong. So they brought in a checklist for these 5 critical steps. And they trained up the doctors and nurses in a particular hospital to use them. And the infection rate dropped from, I think, about 10% of patients who had these central lines to effectively 0. They had something like 2 in a period of months. So they were able to show that they were more or less eradicating these errors of ineptitude for this one particular procedure. So I think there are ways that we can use this kind of thing in SRE as well. So this is what the surgical checklist looks like. This is the World Health Organization Safe Surgery Checklist. This is not a manual, right? This is a checklist. This is not telling you how to do a surgery. This is not the point of these things, right? Because people go to school for years and years and years to learn to be surgeons. They're not going to learn it for a checklist. And there is no school for SRE. Many of us have backgrounds in computer science, software engineering. Some of us have come into SRE through other means. But we've all been at this and we've all developed expertise, right? So we can't write a checklist to tell you how to be SREs, but can we write a checklist to make you remember stuff at the right moment to be better SREs? Maybe we can. This is just one page, but it's quite powerful. So if you look on the column to the right, you'll see there's a part that says, instrument, sponge, and needle counts are correct. That's a small line, but that's saving people from having sponges or God knows what surgical implements sewn up inside of them. There's another thing on the left-hand column that says, risk of greater than 500 milliliters of blood loss. Did you plan for that? Do you have a contingency plan? It's not telling you what that plan should be, but did you think about that? Because that's one thing that it's very easy to just overlook in the moment. Right, so nobody likes process, right? And I don't want to invent ITIL for SREs. Some process is going to put you in a box. It's going to keep you from your freedom. We don't want to do that. I think that excellent process can set us free to live our best lives like these cows in my wonderful homeland of Ireland. So an SRE design review checklist. I think it could look something like this. And this is sort of what I do when I sit down to look at a piece of work and think about it, right? Who, what, and why? Why is this change being made? Who else is reviewing this document? Does this all look good? Alternatives considered. Stickiness. What about this design is going to be hard to change later? Are we okay with that? Have we fully considered what parts of this we're going to be stuck with, or at least that's going to be very expensive to change? Data. There's a lot of stuff about data. Data is like stateless services. They're easy. Data, difficult. Complexity. I think part of our remit is always to keep complexity under control. Scale and performance, operability. How easy is it as a human to be part of this system? How is it working with me? How can I work with it? And robustness. Robustness, as I think, is what most of us focus on when we do sit down to look at a system. We ask how it's going to break, and that's very important too. So who, what, and why? So I think one of the most common experiences, you sit down and you read someone's design and you kind of go, okay, I don't quite understand this. That's okay. Software systems can be complicated. It's very possible that you don't have all the context that that person does. And if you find yourself in this situation, I find that the best thing is to send the person some questions and sort of to say, hey, I didn't quite understand why this change. I didn't understand why this part here. Get clarification before you start moving on, right? Do you understand the goal of the change, right? This is like when we actually write, code, at the level of code. It's very common to see, comments that say, well, I am doing this and then I'm doing that. And say, yeah, well, I can read that from the code. Why? It's not obvious to me why this is happening. So again, like in designs, we want to explain the goals of things and the rationale for doing things particular ways. There's no use saying, well, the system will do A and then B and C, but if you're not making it clear why, what is the requirement that we're trying to solve here? Why have I been asked to review this document? Is this somebody on my team or a partner team? Is there some particular perspective that I'm being asked to give here? If maybe there isn't. Maybe you're just being asked, as a sort of a general interested party, but maybe someone says, hey, Laura, I know you know a lot about networks. I want you to particularly think about that when you review this. Has every affected team been asked to review this? Particularly when you work in a very large, complex organization, as a lot of us do. Sometimes you'll see, okay, well, hey, this design is totally going to impact this thing over here, or it's very similar to this system over here. these people should talk. Privacy or security reviews. Most of us are not experts in that field, and sometimes designs do warrant extra thinking about that. So it's worth pointing that out if it seems to be an issue. And I'm going to call out to tomorrow's closing keynote talk, which we're going to talk a lot more about this. Who might be harmed by this system? Is this system potentially going to do something that's going to be harmful to users, harmful to other groups of people? Is that okay? It's not our primary job, but I think every engineer needs to be a defense in depth against harmful systems. Alternatives considered. People fairly often skip over this, but especially again in large organizations, you can have this very unhealthy proliferation of very similar systems that do similar things. You do not want to end up in an organization where you are trying to run 12 different types of key value stores for no reason. Because then you can't leverage any sort of uniform tooling or any uniform processes about it. People who are moving from team to team don't already know the tools. It's just bad. If there was an alternative considered and it wasn't deemed to be workable, did the author of the document actually go and talk to the system owner? Because sometimes a conversation can actually sort of point out that, hey, okay, we didn't think this could work, but it could work. So it's always worth talking to people. Stickiness. So again, what is going to be hard to change later? So one of the things that I have seen to be most painful over the past couple of decades is where you write a system and you allow your users to sort of arbitrarily extend parts of your code. So what that is effectively sort of an unconstrained creep of your API to be your whole system. And that gets you into a complete state of paralysis. Like, this is terrible. Do not do this. Think very clearly about what the API is that other people are going to be using, because put yourself in your own shoes, maybe, or your post the next person's shoes 5 or 10 or however many years down the line. You're going to be trying to turn down this system at some point. And if you're in a big org and you've got a bunch of users who've sort of written a bunch of custom code hooking into wherever, you're going to have a very bad time with that. Another thing is where you have system behavior that isn't very well defined. That can be, if people will start sort of depending on it, and again, it can be quite hard to move on to the next thing. Data models, they can make things quite sticky as well, particularly thinking about management of entities, management of identity. That can be quite a painful thing to change later. And it's not always possible to predict all the problems that are going to happen here. But like I said, I think putting yourself in the shoes of yourself in a few years when you're trying to migrate everyone off this thing can be quite useful. Data. This is sort of the meat of it, right? Hopefully, after reading any good system design, you can accurately describe how data comes into the system, how it's read back, how it's accessed. Because, the flow of data is really the hard part of distributed systems. If you can't describe the flow of data, then I think you need to go back to step 1, because I think you don't quite understand what the system is doing. And it's time to ask for clarification. Data consistency requirements. They're very often not clearly articulated. How consistent does a particular piece of data need to be in a distributed system, and why? It's also worth thinking about the semantics of the data that the system is dealing with, right? So one of my favorite examples of this is if you look at the original design for the Google file system. It is not a generic file system. It's an append-only file system. And this was basically done, I'm pretty sure, to make life very easy, because if you are appending all the time to files, then you've only got a very small percentage of blocks in your system are going to be active. And that makes your life much easier when things fail. So, are the consistency requirements clearly articulated, and do they make sense for the application, and have we thought about the semantics of what we're trying to do? For data, very often, a lot of the time, a lot of your data can be recomputed from source. Think about that. When this happens, then again, you may have consistency problems. So If you can recompute your data, that gives you different possibilities for if you need to recover. If your backup strategy or your restore strategy is, hey, we're going to recompute our data, think about how long that's going to take you and how much it's going to cost. So if you can recompute all your data, but it's going to take you, a week, that may or may not be okay. Service level objectives, I mean, it's been the whole buzzword about SRE for the last number of years, and we always talk about them, almost always talk about them in terms of latency and errors. It's also useful to have a service level objective for data loss, because you will lose some data. Nothing is ever 100%. You've got to think about how much data you want to lose, and even if it's like we lost it and then we're going to have to get it back from our backups, which are on tape in a mountain somewhere. Think about that, because that feeds into how many replicas you're going to need and whatever else you're going to do with your data. How long does your data need to be retained? I think this is the core thing to ask. Maybe the answer is indefinitely. This is important user data that they have asked us to store, and we don't ever want to delete it unless they tell us to. If it's logs or something of that nature, do you want to keep that forever? Make decisions about that, articulate them, because these are kind of core key privacy and security concerns. And again, does your data need to be encrypted at rest and in transit? That's not something that we think about explicitly enough, and we should, because it's not necessarily easy to do. It comes with a cost as well. It comes with a financial cost to encrypt and decrypt data. And you have to think about key management and all these other concerns. So it should be thought about. And of course, you don't necessarily always get this for free. Like I think like Amazon Web Services will not always encrypt your data in transit. And replicas for your data, how many? And again, in order to answer that question, you need your service level objective for data loss. Okay, so we were SREs, and we know that computers are not perfect and they fail. How are we going to detect that? When one of our systems starts writing garbage data to disk, or a disk gets corrupted in some way, how are we going to detect that? How are we going to reconcile it when we have different replicas of our data that have different values, right? Sharding. Sharding is obviously how we're going to have more data than we can fit on a single disk, right? Or serve with a single machine. How are we going to shard our data? How are we going to deal with growth? Resharding data is still painful for many systems and many organizations. But it doesn't have to be. I mean, there are strategies for doing this gracefully and doing this, in a pleasant manner over time that's not going to wake you up with pages and have you sort of dealing with it when it's on fire. It's nice to think about that when your system is being designed, rather than when your system has fallen over because your biggest shard filled up. How should my data be backed up and restored? Again, for sharded, distributed data sets, that's not actually a trivial question. Access control and authentication. If that's not addressed in a design that includes sensitive information, this is no longer modern best practices. You've got to think about this. And of course, relevant regulations, GDPR, local equivalents, and any data residency requirements. We're starting to see this a lot more in our profession. Particularly those of us who are running kind of cloudy things or things for customers, X as a service. We're very often having customers that say, hey, my data must stay in Germany or wherever. Do we have that requirement now? Is there a potential that we might have that requirement in the future? This is the sort of thing that can, if we go back to our original stickiness thing a couple of slides ago, having somebody come along a year after you've launched a system and say, hey, actually, we need to keep this customer's data in this country. That's one of the things that can be quite painful later on. So that's a good one to think about explicitly. So complexity. Reducing complexity is one of the big SRE job role buzzwords. Who here has something about reducing complexity in their job description? Not that many of you. Interesting. By the way, I should explain this slide. This is a thing called a turducken. This is an American food. Who here is from America? Hi, Theo. Yeah, a few of you. Okay. Has anyone ever eaten turducken? Okay. Oh, a few of you, excellent, yes. So a turducken is a turkey which is stuffed with a duck, which is stuffed with a chicken, and you have to debone them all and roll them, and apparently there's a specific special gravy and stuffing that you have to make for each of the meats as well. So it's a complex. You know, is the complexity worth it? Is the complexity worth it, people who've eaten turducken? Yes, it is, okay. Sometimes the complexity is worth it, but you've got to make that decision, right? So look at the components of your system. You know, how are they interacting with each other? What are the moving parts? Are there clean APIs that make sense? Or are things sort of tightly coupled, reading and writing the same keys in a key value store or something? You know, think about how that looks, and you know, when you're paged for this at 3 a.m., are you going to be able to understand it? Can you make it simpler? Another thing to think about with complexity is sort of overall complexity of the environment. Again, you know, is this design similar to something that we've seen before? I'm not asking here if this is something that could be reused, but you know, again, are we using the same kind of production practices? You know, like at Google, for example, every binary pretty much, you know, it has a status page in the same place that shows the same things. What RPCs are coming in, what RPCs are going out, what are the latency distributions. You know, you can see all the metrics in the same place. So there's a lot to be things logged to the same place in the same way. You know, things. How can you make your system sort of look like things that people are used to? You know, are you using the same kind of building blocks? Are you using the same kind of plumbing? Does the proposal introduce new dependencies? So, you know, hey, I want to start using this shiny new widget. Ah, yes, but this shiny new widget requires you to also start running, say, you know, etcd when I'm running console over here. You know, that's extra complication. You know, now you're running two similar kind of, you know, consensus data stores. Maybe that's worth it. Maybe it's not. But you know, it's just make that decision explicitly. Don't have things kind of coming in through the back door. Okay, scale and performance. So now we're getting into things that hopefully people are pretty well used to. Bottlenecks in the system that are going to limit its scale and its throughput. Don't forget about the write path, right? People often sit down and they say, oh, well, you know, this thing will scale to a bazillion reads per second, and they totally forget that, you know, hey, a couple of times a day, you know, this big batch job is going to spin up that's going to, like, sync a whole load of data from somewhere else, and it's going to do a lot of writes, and, oh, when you start having locking, you know, now you start having contention, and, oh, look what that does to our read throughput now, you know, I've lived this, I'm sure people have lived this. This is not so good. So think about that. And again, the critical path. How do requests fan out? You know, this is a fairly well-known phenomenon. You know, if you have a single request coming in here and then it needs to make 10 sub-requests over there, you know, that's going to be limited because now you're limited by the tail latency of the fanned out requests, right? Well, probably. So, peak load. Do you actually know what your peak load is expected to be? Has the system designer articulated how that's going to be supported? What's the latency SLO going to be? And you know, does that make sense? Capacity planning and load testing. You know, is there a plan for how to do that? You know, particularly with the capacity planning, it's useful to sort of model, again, those bottlenecks that you think that are going to be the gating factors and sort of figure that out in advance. Here's something that we often forget about. What do we depend on? What are we going to be calling? What are the performance limits of the systems that we're going to be using, and what are their documented SLOs? So, I mean, you wouldn't be happy if somebody spun up and started running on, you know, against your system, and then, you know, 6 months down the line, you have your performance gets slightly slower, but still within SLO. They'll probably come along to you and say, your system got slower, and you'll say, we're within SLO, and they said, but we started expecting the performance that you've had for the last 6 months. I mean, this happens all the time, like all the time. Don't be that person. You know, look at the SLOs for the systems that you're depending on, and make sure that that makes sense for you. And not just the SLOs for performance, also the SLOs for reliability. You know, do they work for you? What will it cost? I think controlling costs in the cloud in particular has started to become a fairly big issue in the last number of years. You know, just sort of, you know, spec it out. Think about how much that's going to cost you. very often there's a very big financial difference between using the, very shiny cloud service that, Azure or Amazon or whoever will run for you versus running your own thing. That can make a very big difference. So operability. This is something that we maybe don't talk about as much as we could do. So again, I kind of define operability as how does the system work with me as a human being trying to understand and run it. I think this is something that's, I think it's something that's coming into SRE more and more into our consciousness, that we need to think about ourselves as part of our systems. It's a great thing to aspire to have our systems sit there, run perfectly day in, day out, and never need human intervention, but I know that my systems aren't like that. If anyone has systems that are like that, please come to me afterwards. No, I don't want a new job, I'm good. But the first most basic thing is, how does the design support monitoring and observability? And not just, do I have my 4 golden metrics? How am I actually going to understand what is this system doing? What's the system been doing for the last couple of hours? Like, has it made sort of major decisions about something? How am I going to understand what the state of the world is right now? And like I say, not just the RPC metrics that we would sort of generically slap on any service. What's my cache hit rate? What shards are being resharded or merged, or what things are happening? How do I know this? Which instance is the leader? Which instances are followers? All of these things. How do I, as a human being, go and find that out? At 3 in the morning, when I've been paged, when I haven't had any coffee, think about these things. Some systems are harder to monitor and observe than others are. So, one example, for example, is use of queues in systems. They can really increase robustness. So particularly where you have a system that needs to ingest things constantly, like any sort of monitoring or logging system, you need to be able to accept kind of what's sent to you. People very, very often use a queue on the front end for robustness, and that's a great pattern. However, it does make it harder to kind of understand what the latency of things making it into the actual, backends, the serving backends of your system is. I'm not saying don't use those patterns. Do use those patterns, but make sure that you account in your design for how you're going to monitor things. Again, pipelines are a thing that needs extra thinking about. They're harder to monitor. They need extra thought. So where you have those kinds of factors in your designs, think about it. Third-party system components. I want to use this, new open source widget. Oh no, it doesn't support Prometheus metrics, or it has Prometheus metrics, but they're not telling me what I want to know. That's okay. Go into it with your eyes open, and maybe with a plan to make it better. What tools are going to be available to production operators during incidents? What are the knobs that I can control in this system? And again, we want to make our systems perfect and autonomous and resilient to everything and running without any intervention, but we know that that's not realistic, and I'm going to have to, again, wake up at 3 in the morning and change things. What knobs do I have that I can turn? It's very important to think about early on. Where you have these knobs that you can turn, things that you can change, how is it going to make it clear to me as a human being what's happening in the system? Somebody yesterday talked about the fairly well-known Google incident where somebody sent all of the machines in Google's CDN to disk erase a couple of years back. And how did that happen? Somebody typed a regex into a tool, and the tool said, yep, sure, and erased everything, right? Instead, that tool could have said, hey, operator, I'm going to erase however many thousands of machines, and is that cool? And the operator could have said, well, I expected 16, so no. Operability, how are these tools going to work with me? How are they going to prevent me from shooting myself in the foot? Okay, routine work. Nobody likes, this is toil, right? Every new system introduces new toil. The reason every new system introduces new toil is because new systems, things break, and you tend to have to toil to fix them, right? Until you've, shaken all the bugs out or figured out a way to automate that. And You can also have routine toil of setting up new instances, setting up new users, all these things, right? Doing backups. There's a lot of stuff that you won't have automated yet in a new system. Who is going to do that work? Which team? State that, very, very upfront, because very often, a team will design a system and assume that, some other team over here will do all the actual toil related to it. And they'll be like, no, I don't think so. How much of that work can and should be automated? How much of it should be automated before launch? How much after? Make a plan for your time. The last thing you want to be is in a state where you've launched this system and there's a huge amount of toil related to your new system and nobody has time to actually start automating that because everyone is hands on deck fixing stuff all the time. That's a bad recipe for burnout. It's also worth thinking about automation. Sometimes automation can kind of reduce an operator's view and understanding of the system. So for example, I used to work with a system that could sort of automatically sort of jiggle things around to, if capacity got low in a particular part of the system, it could move stuff around and sort of anneal itself into a better state where things would start working again. And that was completely fine for several months or a year. And then we just ran out of capacity because the system was completely optimized and there was no headroom, right? And that was a case where we built this great bit of automation that saved us all this time and saved us all this hassle. But oh no, we stopped paying attention to how much headroom we had, right? There was that sort of blind spot that it created. So think about automation that you're going to write. How are we still going to understand viscerally, at a human level? How are we going to understand our systems? Another very important thing about operability is how am I going to know? Sometimes detecting abusive users and requests is very hard. Think about these sort of application layer DOS attacks where somebody figures out like a really, really heavy query on your system and just starts hammering that. Or even when they do this completely innocently, right? Somebody will, right? Figure out how you're going to spot that, how you're going to rate limit it or throttle it or what you're going to do. It is easier to do this up front than to do this while everything is falling down. Very often we're depending on vendors or third parties. Are they going to actually be responsive to us when we have support requests? Figure that out ahead of time rather than when your production is burning down. And here's a basic thing. Are all your configurations stored in source control? Hello, Grafana. So robustness. And again, I put this last, and I put this last because I think this is the section that everyone sort of immediately starts thinking about. We kind of think, well, we're SREs. We worry about stuff breaking. And we do worry about stuff breaking. But it's not the only things that we should be worrying about. So the very basics of robustness. How is the system designed to deal with failure at the various physical failure domains? So a device may break, a disk may break, a cluster or availability zone or a data center. What do we expect to happen? How does the design support that? That's usually fairly straightforward. Network partitions or things being arbitrarily slow, those are more tricky. And again, ideally when you have your system up and running, you'll do the right thing from the start and start building in some kind of chaos engineering to make sure that your resiliency goals are met. Manual operations, we talked about toil a bit already, but very often when something falls down, you're going to end up with some manual work like, oh no, a thing failed and it left a mess behind it, and now some human has to go and figure out how to clean up the mess that was left and bring up a new thing. Does the design kind of does it allow for the system to do this work autonomously, or does it expect you to come in and wipe its bottom every time something falls apart? We all know better than this, but we also know that there's always a lot of pressure to ship something. This is the kind of thing that can often happen. Again, budget for this. If you know that this is going to be launched in this kind of state, budget for time to fix it, and try and figure out how much work this is going to be for you. How could I accidentally break this system if I'm on call for it? What's really dangerous to do? Every system is going to be, I think, to some level, it's going to be vulnerable to an operator destroying it, right? We want to make sure that we want to try and stop ourselves shooting ourselves in the foot deliberately, and ideally, we want to be resilient to insider risk as well. I think this is one of those sort of leading edge SRE things, like how do we be on call for our systems, but also also not able to destroy them. Don't necessarily expect people to actually solve this one, but think about it. What's the most damaging thing I could do to this? Okay, I could fat finger my running system and all my backups. What's a mitigation for that? Well, we're going to set up a system that's going to back everything up to, a separate Amazon account with a separate set of credentials, that kind of thing, which is also great if you ever get hacked. Another pretty important robustness concern. What's the smallest divisible unit of work or data in this system? Because that some user will, figure out, well, they won't even figure it out, but that some user will do a thing that will create that, right? It's just going to happen at some point. Whatever the smallest divisible unit is that okay? Is that going to max out your one process? Like this is a known thing in, say, the big table design. You can have a very, 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 very big row in a big table that can sometimes be too big for one tablet, and that is bad. So just think about that, because that's an annoying and painful place to be, and it's nice not to go there. What are the hard dependencies of this system? What do we absolutely rely on? Do we have a caching there? Is that cache? Do we expect to be able to work if that cache isn't there? How do we know that that's going to always be true? Are we going to keep testing that? Soft dependencies, dependencies that your system uses but apparently doesn't absolutely rely on. Those are quite dangerous. They turn into hard dependencies. This is part of your system that you should think about, pretty carefully. And again, if something that your system depends on, is that going to be reliable enough? And if it's something where you're going to say, okay, well, we're going to use this when it's up, and if it's not up, we're going to fail gracefully. We're going to still do something useful. How are you going to make sure that that's always true? How are you going to keep testing that? Restarting your system from scratch. We don't often do this with our systems, but you never know. I mean, sometimes a whole data center reboots. It happens. Power is a thing, right? How do we know? How long is it going to take to come up? Do I have something that needs to, load gigabytes of data or terabytes of data from a disk somewhere? That's going to take some time. Do I need to, rebuild some distributed state? How long is this going to take? Is that okay? Is this a choice that you're happy to live with? Go into that with your eyes open. About 8 years ago, I worked on a system, and we had a cache. We had a cache for basically our user database, and our auth servers would load these up on startup, and they would use the sort of the in-memory state to serve. The problem with this was it took about 45 minutes. Then one day, we were coming up to our peak time, and all of them oomed at the same moment. So there we were, sitting there for 45 minutes while that data loaded. This is not a good place to be. Well, if you do this, go into it with your eyes open. So think about how long it takes for things to come back up again if they're down. Also think about circular dependencies. Do I depend on something that depends on me? Because if so, that can be quite the knot to untangle when everything is broken. Don't forget about DNS and monitoring, because people sometimes leverage their monitoring to do clever things with their systems, but sometimes the monitoring might also depend on you if you're a storage layer or something. DNS is also tricky, particularly if you run anything to do with service orchestration or naming. Large spikes in load. Do you have a plan for load shedding? You should have one. Caching. Caching is great. Caching can shoot you in the foot. If you are using a cache, be clear if you're using a cache to make things faster or in order to have capacity to serve. Like, can you serve everything from the canonical backends, from disk or wherever? If you're relying on your cache to exist, just know that it's a hard dependency. Know that when you bring up new nodes, caches do not work as well until they're warmed up. Caches are good. caches, like I say, can harm you. I mentioned before about Google sending all of its devices, its CDN devices to disk erase. That was, okay, sure there was more latency, but everything still worked by and large, and that worked because that was a cache that was there to reduce latency, not a cache that was there in order to serve. Robustness. Is your control plane fully separate from the data plane? If your system is overwhelmed under load, are you still going to be able to change things? Are you going to be able to control your system? Just think about that. Sometimes people will will use the same parts of their systems for doing both things. It's good to separate those very, very clearly if you can. Can I canary this design? Some system design choices make canarying hard. So canarying is obviously when you are going to run one or a small number of instances of your system after a change and make sure everything still works. Can you canary your configurations? Does that make sense for your system? Designs that use a single leader to perform some function of your system. Those are very hard to canary because you've only got one thing that's actually doing work, right? It's meaningless to canary a follower node, and it's also meaningless to canary your leader node because now you've just updated your entire system, right? So, I'm not saying don't use leader election. I'm saying go into it knowing that that's going to make canarying hard. Pretty much one of the last things is, can this system take down its backends by making excessive requests? So the name for this design anti-pattern at Google was called Laser of Death. And you do not want to do this because if you take down your backends, your system is probably not going to work very well either. So think about your outgoing requests as well. And if I'm a very big service and I'm making requests to a service that's more limited on my backend, can I put in some safeguards to rate limit that? Can I cache things if I'm making repetitive requests? That kind of thing. Another thing to think about is hotspotting. It may be that you're making requests of a backend that has plenty of capacity, but you're hammering one single instance of that with very repetitive requests that are hotspotting a particular shard. Okay, so our very last robustness concerns. Can this system autonomously drain capacity? So we're all building a lot more automation in our systems. We're trying to make our systems, run themselves, and that's a great thing to aspire to. But if your system can drain capacity, so take capacity out of service in some way, you're setting yourself up for potential for the system to entirely drain itself. So just think about how you've mitigated that risk, not only in terms of monitoring and alerting, but also in terms of, again, how is a human going to understand what's happening and be able to intervene? Can the system autonomously initiate resource-intensive processes like large data flows? So what I'm talking about here are things like systems where you have n replicas of data and you've got shards copied hither and yon. What happens if you lose a chunk of your shards? They're all going to start copying data to get back up to the minimum number of replicas for each piece of data. Is there any kind of throttling on that? Because that's something that could happen. Okay, I've lost 10% of my shards on this data store, and I could still serve fine. Oh, except for now they're using all their bandwidth copying data. So stuff like this can bite you. Gossip protocols are well known again for this sort of something happens and then they get in a flap. They start sending traffic everywhere. Can this system create any sort of vicious cycles in that kind of way, right? And again, the resource-intensive processes are a great source of that. Like, well, we started copying data, and oh, look, now the bandwidth is sort of being used up, and now things are not responding to health checks because they're maxed out their network cards, and oh, well, okay, look, now the system thinks that this is out of service just because it's so busy, and the system just gets worse, right? So there are lots of ways that our systems can get in vicious cycles. Cascading failure, inter-process or inter-service communication is a famous source of this. Okay, so what did we talk about? We talked about a checklist that you can use to evaluate designs, hopefully. Who, what, and why of the design, alternatives considered, stickiness, what's hard to change, data, everything about it, complexity, how can we reduce it, hopefully, scale performance, operability of how the system works with its humans, and robustness. If you decide to use a list like this, you should adapt it for your local needs. Whatever your organization does, think about that. Skip things that don't make sense. This is not ITIL. Remember, the goal of a good design is to understand the trade-offs that it is making. We are always making trade-offs. Nothing is ever going to be perfect. Understand your trade-offs, understand your risks, make deliberate choices about it. Don't, choose what the badness that you're gonna have thrust upon you. Don't just sort of sleepwalk into it. Bad things will happen. Just have your eyes open. If you decide to do something because it's going to be cheaper and faster, that's okay. Just consciously choose that. Errors of ignorance are inevitable, but errors of ineptitude are avoidable. We're all making a lot of errors of ineptitude, or at least I know I am. But what I think is that maturing as a profession, SRE is a very, very young profession. It's 10 years old? I mean, this conference is about 5 years old. I think that we need to mature as a profession, and I think that part of that is about getting systematic about reducing the way that we make errors, right? So, finally, we are hiring. We do not have a booth here, but you can always come and talk to me, or you can ping me on the USENIX Slack, the SREcon Slack, and just some credits. Images, Pixabay, the checklist Manifesto by Atul Gawande. Tanya Riley reviewed my slides. She's amazing. I intend to put that checklist up on the internet, but I haven't gotten around to it yet, so I will do that before I put the slides up. And this talk is also going to be the subject of a forthcoming article in Login, which will also contain the list. So next quarter's USENIX Login magazine will have this. So, thank you.